What if I told you that there's a rocket engine design out there so efficient it could have made single-stage-to-orbit spaceplanes a reality decades ago? A design that was actually built, tested, proven to work, and then just abandoned. Well, this is the story of the Aerospike, the revolutionary engine that might just be getting its second chance.
And no, this isn't science fiction. This right here is the XRS 2200 linear Aerospike engine, just roaring to life during tests back in the late 1990s. This was supposed to be it, the future of space travel, a totally radical new way to get thrust that promised to be way more efficient at every single stage of a flight.
So that brings us to the big mystery, right? If this technology was so groundbreaking, so incredibly powerful, why did it just vanish? Why aren't today's most advanced rockets all powered by Aerospikes? Well, the answer is this fascinating story of absolutely brilliant engineering and just heartbreaking failure. To really get why this engine was such a massive deal, we first need to understand the fundamental problem that it was designed to solve in the first place.
Okay, so think about almost any rocket you've ever seen. It's got that classic bell-shaped nozzle at the bottom. But here's the problem. That bell shape is totally fixed. That means it's only truly efficient at one specific altitude. Down here at sea level, the thick air kind of pinches the exhaust, but way up in the vacuum of space, that same exhaust plume spreads out way too much. And either way, you're losing precious efficiency.
Now, the Aerospike solution to this whole problem is just pure genius, because instead of trying to fight the atmosphere, it actually uses it. So on the left, you see that traditional bell, right? The exhaust gets shot out from the inside. But the Aerospike, over on the right, flips that concept completely on its head. It's basically an outside-in engine. The exhaust is fired along the outer surface of a central ramp, or what they call a spike. This design puts the Aerospike into this really special category of engines, altitude compensating nozzles. And really, the name says it all. The whole advantage of the engine is that it automatically adjusts itself to the changing air pressure as the rocket screams its way uphill. So how does it do that? Well, this is the magic trick. The physical spike part forms one side of the nozzle, but the other side? It isn't made of metal at all. It's the air around it. As the rocket climbs and the air pressure drops, this virtual bell made of atmosphere automatically expands, keeping the exhaust flow absolutely perfect and the engine at peak efficiency all the way to orbit.
And here's the proof in the pudding. This graph compares the two. So look at that dashed line for a typical bell nozzle. See how its efficiency spikes up in that one little narrow band? Okay, now look at the solid line for the Aerospike. It starts out strong and just stays incredibly efficient across the entire flight, all the way into the vacuum of space. It's just a fundamentally better performance curve.
Now, this incredible potential wasn't just some theory on a whiteboard. Back in the 1990s, NASA decided to bet big, and I mean big, on the Aerospike for its most ambitious project yet, a fully reusable, single-stage-to-orbit spaceplane. So while the idea had been around since the 60s, it really came of age in the 90s for NASA's X-33 program. Engineers at Rocketdyne took proven hardware from the legendary Saturn V's J2 engine, and they adapted it into this new, linear Aerospike design called the XRS 2200. And let me tell you, these things were powerful. A single one of these XRS 2200 engines produced over 200,000 pounds of thrust. The plan was to slap two of them on the X-33 vehicle, and by all accounts, the tests were just a roaring success. And, the X-33 was just the half-scale prototype. It was the warm-up act. The ultimate goal was this full-scale orbital vehicle called VentureStar. It was supposed to be America's next-gen space shuttle, powered by 7 even more powerful Aerospike engines. This tech was right on the verge of actually happening. And this brings us right back to our mystery. We have a proven, powerful, hyper-efficient engine, ready to go for the next generation of spaceflight. So what on earth went wrong?
Well, the really crucial point is, it wasn't one single thing. The engine itself, yeah, it had some challenges, but they were probably solvable. The spike was heavy, and its huge surface area needed a really complex cooling system. It also had this known performance dip as it went transonic, approaching the speed of sound. But the killing blow, that came from somewhere else entirely.
See, the X-33 vehicle it was supposed to power relied on this revolutionary, but ultimately flawed, composite liquid hydrogen tank. And that tank just failed over and over during testing.
So in 2001, with costs skyrocketing and no fix in sight, the entire X-33 program was canceled. And the Aerospike engine, which had passed its test beautifully, was grounded right along with it.
For almost 2 decades, the Aerospike just seemed like a relic of a future that never happened. But now a whole new generation of space companies is bringing it back from the dead. I mean, just look at this list. You've got companies in Spain testing Methlox Aerospikes. Here in the US, you've got Stoke Space building a reusable second stage with a full Aerospike ring. And just this year, a German company achieved the first ever in-flight ignition of one. This isn't some historical curiosity anymore. It is a full-blown global resurgence. And this gets to the heart of why it's all happening right now. You are looking at the exhaust from an engine that was designed entirely by an AI and then 3D printed out of copper as a single piece. Technologies like these are solving the exact problems of weight and cooling complexity that grounded the original engine all those years ago. So, that leaves us with one final, tantalizing question. The fundamental physics that made the Aerospike so promising in the first place, that hasn't changed a bit. But the tools we have to actually build it, they've been completely transformed. So will today's innovators, armed with AI and 3D printers, finally be the ones to launch the Aerospike from a historical what-if into a working reality? You know, we might just be about to find out.